lecturers last week complimented us on how on time and everything, and that just made me feel great.
I know the birthday time, 7 minutes. All right, maybe we can go ahead once people have settled. How's everyone doing? Good. All right. Awesome. So welcome back. Woo! All right. Welcome back. So it's a great pleasure to introduce our next lecture and lecture subject material. Of course, the interface between particle theory and astrophysics has always been incredibly rich and a source of powerful developments. But I think we're in an era where this is even more true, both because the status and promise of astrophysical observations and just the depth of theoretical possibilities are really at the point where there's an immense amount we stand to learn about microscopic physics beyond the standard model and within the standard model from astrophysical observations. So who better to tell us all about this than Katelin Schutz, who is currently the Canada Research Chair in Astrophysics Beyond the Standard Model at McGill University. Before that, she was a Popplelarter Fellow and a NASA Einstein Fellow at MIT. And before that, she was a APS Saccharide Dissertation Fellowship recipient for her dissertation at UC Berkeley. And so it's a great pleasure to turn it over to Katelin.
Yeah. Is this thing on? Can you guys hear me? Is it on?
Is the green light on?
I think so.
Yeah, it sounds.
Yeah, you guys, it sounds like it's good. Cool. Hi guys, I'm Katelin. I'm going to tell you about astrophysical probes of fundamental physics. I actually have this kind of unique story relationship with Tazi because I actually started graduate school as an astro person, and it was only kind of, at the end of my first year of graduate school, kind of start of my second year, that I transitioned to maybe dipping my toe in the water of particle. And then at Tazi, I actually switched advisors, so made the full transition into particle. And so Tazi has a really near and dear place in my heart of enculturating me as a particle physicist. So it's really special for me to be back here. And I want to also make a quick note about the title here, because as I was sort of sitting down to prepare to tell you guys about this topic, I kind of realized this is an insanely broad topic. And I was like, well, I don't really want to tell them about, astrophysical constraints on variations of the fine structure constant, although that is very interesting, okay? But it's just not my cup of tea personally. Don't want to yuck anybody's yum. So I came up with the following modified title, which is Astrophysics Beyond the Standard Model. So we're going to be mainly thinking about, particles, okay? So we're not going to be doing like any tests of gravity or modified gravity or anything like that. We're going to be talking about particles. And even that is a very, very broad topic. So I just want to sort of start with kind of setting my intentions or giving kind of a mission statement to these lectures. Okay, so it's a really big topic, like I said. I'm definitely not going to be able to do anything super comprehensive. So what I've tried to do for you guys is I've tried to curate a selection of topics that I think kind of highlight the diversity of not only the different astrophysical systems we can use, so the ones that I'm going to tell you about are going to span like 20 orders of magnitude in length, okay, but also some of the different types of models of beyond standard model physics. There's also a huge breadth of things we can test there, okay? Related to this, astrophysical observations are usually happening at energy scales that are much, much lower than what we can access with other kinds of experiments, for example, colliders. One exception to that actually is astrophysical neutrinos. Okay, those can be like at insanely, super high energies. I'm not going to focus on those during my lectures, but that's kind of one loophole to what I'm saying. And so because we're going to be talking about kind of lower energy scale physics, one thing that I think is a really helpful organizing principle to think about, what we can test at those scales is kind of bottom-up effective field theory. So in other words, just kind of writing down all of the operators that have kind of dimension 4, maybe going up to dimension 5, and thinking about those operators as being portals. They're particles, but they're portals. Someone should capitalize on that. These are going to be my portals to the beyond standard model physics that I want to search for. Okay, so in light of the above, the breadth of topics we're going to talk about, the breadth of models, the EFT approach. Okay, for all of those reasons, I'm going to try to cover ground as quickly as possible. And so to aid me in that effort, I'm going to be doing things kind of order of magnitude style. So 3 is going to be equal to 10, is going to be equal to pi. I'm not going to, don't hold me to any factors of 2, okay? And lots of spherical cows everywhere. So we're going to be making a lot of simplifying assumptions. My goal is kind of just to help you guys know where to look if you want to take a deeper dive. Finally, let's have fun with it. I've heard you guys are a pretty interactive group of students, so definitely don't be shy to ask questions if you want anything clarified or want to know more. I would ask, actually, if you could maybe because I'm new here, and you guys have all been here for 3 weeks, and you kind of know each other, but I don't know you. So when you ask a question for the first time, maybe you could say your name, your institution, and what you work on. I think that would just make things more fun for me. And I kind of like to know who I'm speaking to. OK? Any questions about any of this, my mission statement? OK, cool. So if not, this is kind of the outline of my lectures. So here, I'm kind of drawing a very schematic Feynman diagram, if you want to think about it that way, where I'm going to be thinking about ways that the standard model, so in other words, astrophysical systems, and how it can talk to physics beyond the standard model. Okay, this blob is some kind of blob. I don't know what's happening inside of there. And depending on which way I have time pointing in these diagrams, I can have different kinds of processes. So I'm going to be kind of covering 3 qualitatively different topics. One of them is going to be where I read the time arrow in this direction. Okay, another where I'm going to read it in this direction. And finally, I'm going to read it in this direction. In other words, the topics are going to be make it, break it, and shake it. Okay, so that's kind of the organizing principle of my lectures. The shake it includes gravity. So I don't know whatever's happening in terms of quantum gravity, in terms of this blob, but yeah, we're going to also include that because there's a lot that actually just purely gravitational interactions can tell us about physics beyond the standard model. OK, any questions about the organization? OK, just wrapping up my housekeeping. You guys are good? Cool. All right, so yeah, without further ado, topic number 1, we're going to make it. So in particular, again, this is there's so much I could talk about here. For this kind of topic, I'm going to hone in on the following model system. I'm going to want to talk primarily about stars and also compact objects. And some key references, if anyone wants to learn more about this topic, I'm going to recommend you 2 textbooks, one by Rafael and one by Dan Maoz. I think they're both pretty solid. And if you want any more literature-based archive numbers or anything like that, definitely feel free to ping me on the Slack. OK. Oops, all right, great. So, all right, this is the first topic. So let's get into it. Oh, actually, before I start writing stuff on the chalkboard, I'm going to do the following. So I've been told that you guys can't see to the bottom here. So I'm going to start moving my hand up. And once the back row can see it, can you guys yell out? OK, ready? OK, here's where I'm going to, OK. Here's what I'm going to do. I'm going to eyeball it. All right, I won't write below there. OK, cool.
You can write below there on that board, because that board moves.
Oh, good point. Where did the eraser go? Oh, there it is. I'm just doing it on the back one so that I can so here's what I'm going to do. This is my arts and crafts side coming out. So this one I'm just going to, slide down kind of, I guess, to all the way to the bottom. And then as I start to kind of approach that point, I'm going to move it up so that people can see it. And then when this one's elevated, I'm going to slide this one, and I'm just going to bring it down to here. OK, that's going to be my MO. All right. But yeah, I'll copy the other line as appropriate for that board. Okay, cool. So let's get into it. We're going to make it. So we're going to talk about stars as factories for BSM. Okay. So you may be wondering why stars? Right? And I guess they're remnants. So there's a few reasons, a few good reasons for considering stars. So typically their temperature can be on the order of sort of 10 keV for regular stars, or up to around an MeV for supernovae. Okay, and so this implies the production of light particles is possible. Okay, and actually there's some caveats to this statement because it's actually not all about the temperature in some situations. Sometimes actually the density of the star is really the determining factor in terms of the kinematics of how you can produce particles, but we're just going to treat this as a heuristic for now. Okay, so any kind of particle that you may have kind of below these kind of characteristic scales can in principle be produced inside of a star. Okay, so that's just a kinematics argument. There's more reasons though. So another reason is that the volume and age of stars mean that you can have rare processes okay, that couldn't be seen elsewhere. Okay, so we can kind of think of stars and their remnants as kind of existing out in space, much for our, utilitarian purposes of doing a particle physics experiment. And so any effects of the production of light particles can be amplified by the volume of the star, right? It's much larger volume than what you could, say, make in a collider. And also, some of these effects are cumulative. So the fact that stars can be, billions to tens of billions of years old means that we can see the cumulative effects over a much longer kind of lever arm in time, okay? Okay. Put maybe colliders as an example. Okay, and then final point that I think stars have going for them is that they are very observable. So there's an observability kind of angle to it, and also a ubiquity. So we're able to see stars out to very, very large distances because they're very luminous. And so we are able to probe them over a large, large volume of our universe. And so that makes them relatively ubiquitous. And in some cases, we also have proximity working to our advantage, the prime example of this being the sun. Okay, so a lot of searches for beyond standard model physics actually use the sun as a source, and then you try to detect on Earth the byproducts of this production. Okay? So these are kind of all things that I think stars have going for them, but this also may raise the question, stars, right, they're this kind of big ball of plasma, everything's interacting a ton, you've got all these nuclear reactions going on, so is there even an opportunity here? Can stars actually be impacted by BSM physics when you have all the vanilla standard model stuff going on? The answer is yes. So the question, will rare processes be overwhelmed? How do you spell overwhelm? Overwhelm? Okay. By the standard model? The answer is no. Good thing I'm not a spelling teacher, physics teacher. Okay, so no, or not necessarily, I guess I would say is the answer to this question. So let's actually plug in some numbers and try to quantify this. All right. So now we're going to do this crafty little trick here. Cool. All right. Actually, no, you know what? Before we do that, I'm going to do this. I like to use Wolfram Alpha a lot, so we're going to do it live. So what's the mass of the sun? Good. A plus. 10 points for Gryffindor. It's around 10 to the 30 kilograms. Okay, cool. What's the radius of the sun? And again, I'm just kind of using the sun as kind of a proxy for like a typical star, which turns out to actually be a pretty good proxy. Okay, radius of the sun. Okay, some number of meters. Okay, I'm going to call that 10 to the 9 meters. Interestingly, the density of the sun is actually really similar to the density of water. Okay, it's kind of surprising to most people. Just to show my receipts, mass of the sun, I'm going to divide it by the radius of the sun cubed, and I'm going to maybe put a factor of 4 here. So it's going to be 4 pi over 3, but pi equals 3. So, and we're going to get something. Oh, it didn't like that.
You need parentheses, including the 4 and the radius.
Yeah, I mean, sometimes Wolfram Alpha is finicky about needing parentheses or not, so it's just vibes. Yeah, so okay, about a gram per centimeter cubed. So that's like really similar to the density of water. Okay, so that's kind of surprising. Okay, cool. So now most of the mass of the sun is actually in protons. It's like 10% neutrons, but like this is order of magnitude style, so we're gonna ignore that. So let's take the mass density of the sun, and then now we're gonna divide that by the mass of a proton, because then we're gonna get the number density of protons. Did it even interpret that right? Yes, it did. 10 to the 24 per centimeter cubed. That's kind of what matches my notes, so that came out correctly. So that's kind of the number density of protons in the sun. We think the sun is charge neutral, so we should actually have the same number density of electrons in the sun. And so, okay, we have some electrons. If you have electrons, then the primary interaction that's going to happen at like low energies is actually just Thomson scattering. So if you have a bunch of photons, a bunch of free electrons, you put them in a box, that's what's going to happen. And so how's the rate going to go? Again, order magnitude style, dimensional analysis style. Well, we just computed the number density, so that's going to be helpful. What are some other things that might be helpful? Speak up. Cross-section, good. So we need the number density, we need the cross-section, and we need one more ingredient. Speak up. Velocity, good, velocity. Okay, this is actually, formally this is the relative velocity. So we just calculated this. It's whatever Wolfram Alpha says it is, okay. Sigma, anyone know the Thomson cross-section off the top of their head? That's okay, I don't either, but Wolfram Alpha knows it. So let's multiply this by the Thomson cross-section. And so this is the Thomson cross-section. And VREL, I mean, so this is electrons and photon scattering, so VREL is just going to be speed of light, right? Because it's photons. So let's throw that in there and see if we get something that has dimensions of a rate. It's thinking. Cool. Yeah, the Thomson cross-section, yeah. Yep. 10 points for Gryffindor. I have that in my notes too, but I can never remember it. So Wolfram Alpha can though. So great, that's a rate. That's something that has units of rate. It matches what I have in my notes, so everything is good. 10 to the 10 per second. So that's the average rate for a photon to scatter off of an electron, a free electron in this plasma. Okay. What does that mean in terms of how far can a photon actually go? Okay, so I think if we just get rid of the speed of light, that's either going to have the right dimensions or inverse of the right dimensions. Oh yeah, we got to invert that. So yeah, how far does a photon go in that intervening time? Yeah, about 1 centimeter. Okay, so I'm going to call that LMFP. This stands for mean free path. It's just like how far does it typically go before it scatters again. And what we just found over there is that this is on the order of 1 centimeter. Okay, so that's, okay, well, I don't need to look it up to know that that's a lot smaller than the radius of the sun, right? Hopefully I don't need Wolfram Alpha to tell me that. So that's much, much less than our sun. So what that essentially means is that photons can't stream out of the sun or other stars. Photons actually need to random walk out. Okay, so photons random walk out of the sun. Okay, and for a random walk, maybe you remember this from like a stat mech class or something. I don't know. If anyone wants me to give a heuristic argument, I can. But the distance that you're able to go from random walking is going to be proportional to root n times your mean free path. And this is the number of steps. Okay. So if we want a photon to go from the center of the sun to the edge of the sun to random walk outside, so for this, I can put the radius of the sun, and I can divide that, so I can move the mean free path to the other side.
Is there any way to make the size of what you're displaying
Oh,
big? Because
great
the
question.
text in the window is pretty tiny from the audience.
Yeah.
There we go.
Booyah. Cool. So I'm going to put some extra parentheses around here too, just to like be on the safe side. Okay, so I'm going to move out to the other side. I'm going to square it. We're going to be extra careful with our parentheses today. We're going to square it. And yes, that matches what I have. So n is like 10 to the 21 steps, okay? Which, if I multiply it times my mean free time, so my mean free time is like the rate, but to the -1, okay? So if I take that number, okay, and divide it by the mean free time, which is like 10 to the -10 seconds, okay, then basically what I'm going to find is that this corresponds to 10 to the 4 years. Hopefully you guys will take my word for it. I could do it there, but the parentheses are becoming a little cumbersome. So 10 to the 4 years, around 10,000 years. Meanwhile, if I were to just say, I'll go over here. If I just take the radius of the sun and divide it by the speed of light, c, I'm going to get something that's on the order of 1 second. Okay? So what this calculation here tells us is that the standard model is really, really bad or really slow at transporting energy inside of stars. But if you have something that can just stream freely through a star, okay, that's going to be a much more efficient way of transporting energy out of the star. Okay, so there's kind of competing effects here. Okay, you can have something like the standard model photon, which is very strongly coupled to the plasma. Okay, so it's really, really easy to make tons and tons of photons inside of the sun. But then the price you pay is that they take forever to get out because they have a short mean free path. Meanwhile, if you make something that's really weakly coupled to the plasma, it can leave the star, many orders of magnitude faster. But on the flip side of that, you then pay a penalty because now it's much more rare to produce that thing. So there's kind of some give and take there. There's an optimization problem. And that's That's kind of where the rich physics is, all right? I will say that there is one exception to this. So photons are not the only way of transporting energy out of a star. We also have neutrinos. So neutrinos have a long mean free path. Okay, so much like what I was just saying, you kind of pay some penalty for the fact that it's the weak nuclear force. So you have some G Fermis in there that are going to make neutrinos really, really hard to produce. But once you actually produce them, they stream out. And so they're actually an important source of energy loss. Okay, so they are important. Okay. So I would say for many years, actually, for this reason here, the state of the art was to take my BSM physics process that I care about looking for and equate that with the energy loss from neutrinos. Okay, and if I set those two equal, then I can say, well, you know, if my BSM is below the neutrino one, then the neutrino one is just going to swamp me. If my BSM one is above the neutrino one, then okay, maybe I have a chance to look for it. This is called the Rafelt criterion, and this was like the state of the art for many, many years. And it's kind of reasonable if, you know, all you have access to is kind of like, you know, integrated information over the entire star. But actually, something I'm going to try to, you know, show to you or convince you of is that actually, in the advent of better data, qualitatively different data, as well as a lot of computational advances from stellar evolution codes, we actually can do better than that in many cases. Okay? Yeah.
How much does all this depend on all like the nuclear jump that's happening in the stars?
Yeah, it depends a ton on that, actually. Oh, sorry, thank you. And I know you're Rickup because we overlapped, but yeah, also ask again people to like say their name and affiliations and stuff. Yeah, so Rickup just asked, to what extent is this affected by a bunch of nuclear stuff happening inside of stars? The answer is yes, it is affected by that. I would say, you know, we have known about kind of the connection between terrestrial nuclear physics and what's happening in stars for many, many decades. And so I think a lot of that has been worked out in terms of the most vanilla conditions or the most important nuclear processes. I think there are some kind of like edges of our knowledge where things could be important, but it's not going to be something I'm going to focus on. And I wouldn't say it's like one of the dominant sources of uncertainty. Yeah, great question. Cool. Okay, so that's kind of just the preamble. Any other questions before we kind of get into more? I want to actually also maybe spend a few minutes kind of, so actually here's a slide that kind of recaps everything I just said. Okay, photons take a long time to stream out. Okay. So eventually they hit the photosphere. That's actually the surface of last scattering of the sun. As you may be able to tell from that nomenclature, I actually, my training was initially as a cosmologist, so I learned cosmology first. And so the way I think about stars is actually like a lot of it is inspired by things like the CMB. So I think of the photosphere as being like the CMB of a sun. That's what we can observe about it. Actually, these days we can kind of see inside of it a little bit better using like astroseismology. Okay, but I would argue that's kind of like the BAO of the sun. So I'm still going to cling to that. Okay, so this is what we can observe. And again, things random walk out. Okay, so what are the stakes here? What kind of BSM physics is kind of the ripest for us to try to constrain using this system? Oh, now it's time for me to erase my mistake, but I have that I can use to guide my eye. Is this working, by the way? Can people, everyone in the back can still see this? Yeah, I'm getting thumbs up. Oh, question here. Okay, nice to meet you. It depends on what you're trying to do. Oh, Thank you. The question was, is this a method for constraining new physics, or can we potentially discover new physics as well? I would say it depends on what you're trying to do with this. It's always easier to constrain than it is to discover. I pray every night that I don't discover something, because that's when the real work begins, okay? I'm kidding, but not really. But yeah, it depends on what you're trying to do. So for example, in some applications of this kind of idea, you might have a situation where you have particles being emitted from the sun and you're trying to detect them directly in your lab. And in those cases, yes, it is possible to say, yes, I have for sure detected, this is the particle, this is my oscilloscope, there's a bump. Okay, that's my very, very naive understanding of how experiment works. Again, I'm kidding. If you're trying to look for indirect signatures, yes, of course, there can always be systematics. There can be weird weird SM physics that we don't understand. So 100%, but it just kind of depends. Yeah. Great. Cool. So again, so what are the stakes? So I'll mention just a few candidates of BSM physics that we can constrain using stars. It's just a few examples. It's definitely not comprehensive. So what are some BSM particles with a long mean free path? Okay. Here are some examples. Probably one of the more famous ones being the axion. Has anyone done lectures on axions during TASI? You guys have heard? I'm seeing some heads shaking no. Oh, that's too bad. Well, for the intents and purposes of this talk, axions, we love them. We're not going to go into why we love them, but we do. Here's the Lagrangian that we care about constraining. Okay, it can have terms like this. Actually, maybe Ken will. Ken, are you going to talk? Yeah. Okay, Ken's got it covered. All right. So Wednesday. Okay, so I don't know if you'll survive the suspense, but in the meantime, here's the Lagrangian, GA and N. Okay, so this is some coupling between an axion and some nucleon. So I'm going to have this d mu A, N bar, gamma mu, gamma 5, because it's axial, so there's gamma 5. Okay, and what else? We can have terms like this, GAEE. It's going to be the same. Oh, whoops, sorry, I'm missing this is not dimensionally correct, so bad lecturer. Messing up my dimensional analysis. There's a 2m nucleon here. Similarly over here, I'm going to have a similar kind of interaction, except it's going to be with electrons. D mu A, E bar, gamma mu, gamma 5, E. Yeah, I have room. Okay, and then there's going to be a GA, gamma gamma, A times E dot B, and this is just describing the interaction of axions with photons. Maybe Ken will go into this more in his lectures, but depending on your model of the axion, you can have these types of interactions with some admixture. For example, if you only have this one, we call this like a nucleophilic. And similarly, this is electrophilic. Or sometimes called photophobic for both of these two. And as you might imagine, this one is the photophilic one. Photophilic coupling. Philic. Okay, and depending on which kind of coupling you are looking to constrain, there's a few different kinds of processes that can be pretty efficient at making axions in the center of a star. Just to name a few, okay, we have different processes that can give us Brem. So let's say you have nuclei scattering. You can Brem off an axion, exchange a pion or something. Or you can have something similar happening, but with electrons and photons. So something like this. Okay, and this can be an electron or maybe some ion that has some charge Z, can Brem off an axion from there. Okay, so those are kind of the main Brem processes. Okay. You can also have this so-called Primakov or Primakov-like processes, so something that looks kind of like this. Okay, this can be, again, some ion, and this is a photon converting to an axion. Okay, so this is making use of this coupling over here. If you actually have an ambient B field around, you actually don't need this part of the diagram, and your ambient B field will just kind of provide for you the background photon. Okay, so that's the Primakov processes. I'm actually going to lift this because it's actually starting to bother my back. All right, so we've got the Primakov-like processes. We've also got Compton-like processes. So we've got this one. Oops. Yeah, this one. Got a bunch of electrons, and you make an axion. This is Compton. Also, there's a bunch of atomic processes. So if you think about an atom as kind of like a bound state, where you have this photon mediating your bound state, okay, you can kind of like de-excite your atom by emitting an axion. Okay, so this is your atomic nucleus. Okay, I'm being a little schematic here, but I'm just trying to give you kind of the flavor of some of the different types of interactions. And again, depending on, what your different couplings are and the relationship between all of your couplings, which could be model dependent, different of these processes are going to be the thing that dominates, okay? But if you only want to talk about one at a time, kind of here are the stakes. Here's what's at stake. Okay, so here we're kind of just focusing on the coupling to nuclei, okay? And here in green, this is neutron star cooling. So we can see that for most of the parameter space, this is actually the kind of dominant thing that's constraining the existence of axions as a state in the spectrum. Don't have to rely on them being dark matter, nothing. This is just a state in the spectrum. Similarly, here's the constraint on the coupling to electrons, okay, from all the different kinds of stars. Red giants happen to be the strongest. We'll talk more about red giant stars. And then finally, here's the constraints on GA gamma gamma. And then again, a lot of these are coming from compact objects like pulsars, but also the kind of more vanilla, if you will, constraints where you have particles coming out of the sun and we try to detect them in the lab. Okay, so we're going to talk about all of this more in detail. This is just a little bit of an amuse-bouche to kind of show you what we're trying to learn here. Okay? Okay, I'm going to try to bring this. Oh, no. Is this the one that slides? Yes, it is. Good. Oh, yes.
Hi, I'm Sam from Casting.
Hello.
Just a question, like in the last plot, where is the QCD axis line?
Oh, gosh. It's probably like here. I'm so sorry. I keep forgetting. The question was, where is the QCD axion line? It's probably somewhere over here, if I had to guess from memory. Yeah. So yeah, for those who know things about axions, you may be familiar with the QCD axion. Stars are generally able to probe parts of the QCD axion parameter space, typically at higher masses, higher axion masses, where the coupling strength is larger. But, you know, we're still talking about couplings of 10 to the minus 13, or yeah, few times 10 to the minus 13. Here's not as good, 10 to the minus 9. But again, that's just the raw coupling constant. So any process you want to do, you have to square that at the very least, if not raise it to the 4th power. So I think that's still pretty good. OK. Yes, another question here.
Yeah, I'm Yanis from Student Belgium. I was just wondering, all of these constraints, they're mostly dominated by perturbative processes, or you also have like kind of Schwinger reflex or whatever?
Ah, great question. The question was if these are all dominated by perturbative processes or whether any Schwinger kind of pair production might be important. Definitely not Schwinger for, I think, the ones that I'm showing here, because that typically requires a large unscreened electric field. But in the next example I'll get to, there will be kind of finite temperature, kind of, yeah, you can't just use 0 temperature QFT, will become very, very important for certain types of particles. So not exactly Schwinger pair production, but other stuff. Good question. OK, so that's just kind of one example. I'll give another quick example, which is, oh, I was going to raise this to be flush with that. All right. Another example is millicharge particles. And I put an asterisk here because there's actually nothing 10 to the 3 about this, 10 to the minus 3 about this. It's kind of a historical name, actually. But yeah, people always ask me about it. And again, I'm not going to talk too much about the model for this. But if you have a particle that has some small effective charge and it talks to the standard model, that's a dimension 4 operator that I can write down. So again, I'm going to embrace this bottom-up effective field theory point of view. So the Lagrangian for this is going to look something like I have some Q here, which is my millicharge. OK. And it's going to talk to some particle chi the same way that like electrons talk to the photon. Oops, sorry, it's gamma mu. So yes, here's actually a really good example where you can't just use kind of vacuum QFT. Stars are not a vacuum, obviously. And in this case, it really matters because the dominant actually mechanism for making these kinds of particles is the following. Inside of a plasma, photons actually pick up a mass. So I'm going to give this a little star just to highlight the fact that this is the standard model photon, but its dispersion relations have been altered by the presence of this medium. And unlike in a vacuum where photons are absolutely stable, now because it has this modified dispersion relation, it can actually decay to a pair of these guys. All right. So this is called plasmon decay. OK. And yeah, if this sounds super exotic, that's because, well, on the one hand, it kind of is. But on the other hand, it's actually really not so exotic because it's not often talked about outside of the realm of stellar astrophysics. But something like this actually happens in the standard model. So in the standard model, you can have a process like your plasmon goes to a pair of E plus E minus. And through the 4 Fermi interaction, it can actually decay to a pair of neutrinos. Okay? And this actually has been observed. And we will actually talk about that in these lectures. So we will talk about how that's been observed to happen in stars. And so hopefully, yeah, this example maybe highlights the question that we just got. You do kind of clearly have to think about thermal field theory in this context. Yeah, question here.
Hi, Austin from Oregon.
Hi there.
What is the typical invariant mass scale of the Aushel gamma there in stars?
So this is on shell. This is actually on shell, this gamma.
Okay.
Sorry, it's on shell in the sense that it's a mode of the plasma that can propagate without being dissipated. And it doesn't have an invariant mass because the plasma has a reference frame whose rest frame actually violates or breaks Lorentz invariance. So it's kind of a mass, but it's not. You shouldn't take that too literally.
Okay.
Yeah.
How much energy do I have here?
Great question. So it really depends. In a star like the sun, it's kind of order like hundreds of EVs. So anything lighter than half of that you can make in the sun. In other systems, it can be higher, and it's actually proportional to the density, or the square root of the, the square root of the density. Yeah, great. Okay, cool. Final example that I want to talk about is the dark photon. And I'm going to specifically hone in on the kinetically mixed one. Okay, you can have like B minus L or L mu minus L tau if you want, but we're going to just talk about this one because this is a really interesting one. The Lagrangian for this looks something like, you have your usual kinetic term for your regular photon. You have the equivalent, sorry, I'm saying F squared here. I'm being a little cavalier. I think you guys know what I mean. Minus a quarter F prime squared. That's my dark photons kinetic term. We have a kinetic mixing, which is parametrized by epsilon, FF prime. So again, in the spirit of bottom-up effective field theory, F has dimension 2, F prime has dimension 2, so this whole thing has dimension 4, and so this is just some dimensionless parameter that parameterizes the mixing. And then maybe, this is optional, but I'm going to add it if I want, you can add it if you want. I'm going to put in a hard mass term, okay? This is called a Struckelberg mass. Okay, and it's this trick that you can do with vectors where you are allowed to, stick in a hard mass like that, and it doesn't break age invariance or anything. It doesn't break anything. It's all good. If you prefer, you can also look at a Higgs generated mass term as well. But that tends to be a little bit more complicated, so I'll just focus on this. And in this situation, which again, it's some dimension 4 operator, you talk to some string theorists and they can say some words about why this is motivated, but I don't super care about this because I'm an effective field theorist. And in this situation, the dominant process, I'll try to draw it down here because it's a skinny process. The dominant process is actually when this plasmon mixes with my dark photon. So this is when MA prime is equal to what I'm going to call the mass of my photon. And here it's in quotation marks, again, to kind of emphasize this point that you shouldn't think about it as a literal mass, but you can kind of make the analogy, okay? Okay, so the way that you actually get this is super interesting. It involves a lot of thermal field theory, and there's some non-trivial rotations you have to do to kind of rotate away the kinetic mixing term and make your kinetic term canonical and blah, blah, blah. I'm not going to actually get into that in these lectures, but maybe for for future organizers of TASI, I think actually having thermal field theory applications to astrophysics would be a super interesting topic for perhaps a future TASI. Cool. So, so those are a few of the lowest hanging fruits. Oh, again, let me show you kind of what's at stake. So here are the stellar constraints on dark photons. The plot on the left, I actually should probably email Kieran because I think it's not quite right. So here's like the whole kind of low mass parameter space below kind of 100 keV. And you can see that like astrophysical constraints are like really dominating pretty much the entire time. There's like this little caret over here where you can maybe do better with terrestrial, but again, especially over here, this is the solar, and GC stands for globular cluster, so this is a constraint coming from looking at globular clusters of stars. And again, this is a dimensionless number, this epsilon kinetic mixing, and it's like 10 to the minus 16. So again, like you want to take that process and square it, that's going to give you 10 to the minus 32. So that's pretty impressive what you can do with the star in terms of constraints. The reason I think something's wrong with the shape here is because this is the solar one, and this is the globular cluster one. But I actually think that it's missing the tip of the red giant branch. So there should kind of be like 4 little prongs sticking out over here. So I'm going to email Kieran. And then question here.
I'm Peter from the University of Zurich. So if these processes existed, wouldn't we have already seen them, for example, in an E plus E minus collider? That looks like E plus E minus collision to me.
Great question. So the question was, if this process could happen, would we have not already seen it in an E plus E minus collider? I don't have a quantitative thing. So actually, I think what would be happening in an E plus E minus collider would be off of the plot. I think this is actually better addressed not through looking at dark photons, but actually looking at millicharge, where I had the foresight to anticipate this question. So here's the latest constraints from millicharge. This is the tip of the red giant branch constraint. Again, we're going down to charges, effective charges, kind of a few times 10 to the minus 15. So again, very impressive what stars can do. I've kind of very, very schematically tried to position these plots such that they kind of like are forming a continuum. So this plot cuts off at an MeV, and this plot starts at an MeV, and this plot ends at around 10 to the minus 8, and this plot starts at 10 to the minus 7. And so that's kind of what an E plus E minus collider can do in terms of like, it's a very different range of masses, first of all. So for the millicharge case, as well as for the dark photon case, I don't know of any terrestrial experiments that necessarily have that kind of resolution to go down to such light masses. But also, the couplings that can be constrained are just so many orders of magnitude below what you could actually test at a collider. So this is really a very complementary type of probe. It's like looking at very different parameter space, but I do think it is really impressive just how many orders of magnitude you can really go down here in terms of the charge. I think that's pretty impressive. So, oh, yes, question back here.
Hi, I'm Victoria from UC Irvine.
Hello.
If we were to discover the dark photon, is there a way to know if its mass comes from circular mechanism or the Higgs mechanism?
Yes, when you have the Higgs.
Can you repeat the question?
Oh, yes, thank you. I need to get like a little like bracelet or something so I can look at it and it remind me. Yeah, the question was. Thank you. The question was, if we were to discover a dark photon, is there a way to tell if its mass is generated by the Struckelberg mechanism or by the Higgs mechanism or something like the Higgs mechanism? When you have this dark Higgs kind of coming along for the ride, it's not like you can just throw it in there and thoughts and prayers. Like there's actually a strong relationship between the mass of the dark photon, its kinetic mixing, the mass of the Higgs, its VEV, the Yukawa, like all the Yukawas. So there's like a lot of things that have kind of relationships to one another. And actually, you can constrain dark Higgses pretty well as well, because they can mix with scalars pretty easily. So anyway, long story short, I think typically the reason why people are looking at Struckelberg is because it's just a lot less constrained. You can look at Higgs, but it's a little bit more constrained. Yeah. Oh, sorry. Oh, I don't know who was first. Sorry.
I'm Sean from MIT.
Hi.
Is there a reason that it's like natural for epsilon to be small or something?
Same question.
Oh, great question. I'm an effective field theorist, so I don't know how to answer that. But if you talk to some of my string theory colleagues, oh my gosh, I'm so sorry, you guys. The question was, is there a reason to expect epsilon to be really, really small? The answer is, I don't know. I'm an effective field theorist. But if you talk to string theory colleagues, they might say some words like type 2b, string theory, and maybe some of the people in this room have opinions about that, but that's above my pay grade. Okay. All right. All right. Any more questions about the models or what's at stake here? We're trying to set the strongest limits. Oh, back row. Hello. Of which plot? Oh, sorry. So the question was, what determines the upper limit of the plot? Do you mean like this type of plot? In principle, if you actually, so we'll talk more about where some of these bounds come from, but a lot of them come from stellar energy loss. So that it's this argument of like, if I can free stream out of a star, then I can like really affect the properties of that star. But if you crank up the couplings too high, at some point that stops being true because your mean free path is going to be short, and so you're going to be trapped. And so you can still set a constraint, but you have to work harder. Typically, though, before that happens, you're going to run into some other constraints. Yeah. Cool. cool. I love all the questions. Woo! Oh my God, is that the time? Oh God.
Yep, you got about 20 minutes.
Whew. All right. Let's talk about what we can actually observe about stars. So now I've kind of baited you, told you what the stakes are. So what can we even observe? So first of all, we can get the spectra of stars. Here's a typical spectrum. And to pretty good approximation, it kind of looks like a black body spectrum. So here, this is a fit to a black body. Different type of stars are going to have a different effective black body temperature. Okay, so here are the different spectral types of stars. And yeah, there's going to be some atomic lines. There's going to be some deviations from being a perfect black body. But order of magnitude style, this is a black body. So I can measure this. And what I can then do, so I can integrate over all of my wavelengths or all of my frequencies equivalently to get the total flux coming out. Okay, so notice that this is flux. So this is watts per meter squared per nanometer. Okay, so I integrate over the wavelengths. So that gets rid of the nanometer. So now I have something watts per meter squared. That's the total flux. Okay. Another thing I can measure pretty easily about stars. Where did my eraser go? There it is. I'm getting my steps in, eh? So something else I can measure. So we can also get the distance actually. And this is especially true in the era of Gaia. Gaia is this really amazing spacecraft that's measuring the positions of stars with very, very high accuracy. And we can get the distance through this parallax effect where we're going around the sun, okay, where we know the distance of the Earth to the sun. Okay, it's 1 astronomical unit. Okay, let's say I have my star over here. And now if I go around the sun, okay, the relative position of the star is going to be different, okay, relative to the fixed background stars. Okay, when I say fixed background, I just mean far enough away. So like if I stick my finger in front of my hand or my finger in front of my face and I close one eye, okay, now my finger's blocking Oliver, but now if I go to the other eye, now my finger is next to Oliver. Okay, so that's how that works. The back of the classroom is my fixed background stars. Okay, so we can figure out this angle because we can do trig. Okay, so we can measure this, and we can figure out using trig how far away the star is if we can measure that. With Gaia, we can measure. Okay, so that's very helpful. Like I'm showing you there, we can also get the spectral flux density, from which we can get the total flux. If we combine it with the distance, we can get the luminosity. Okay, because basically, again, stars, we're doing spherical cows here, so all of the energy that they radiate kind of gets spread over the surface of a sphere. Okay, so if we know our distance to that star, we know the radius of that sphere. Okay, and so we can figure out what fraction of the flux we're seeing, and we can figure out the luminosity. Okay. We can also get the temperature of the surface. I'm going to call that T star. Okay. And from that, we can also actually get the radius of the star. So we're really getting our bang for our buck here. And the way that we get the radius is by saying, well, I know the flux coming out of a black body is pi t star to the 4th over 60. Okay, that's the flux coming out of a black body in natural units. And I can equate that to the luminosity and divide by 4 pi times the radius of the star squared. So that's how I can figure out the star's radius. It's not a direct measurement, it's an indirect. Oh, I'm so sorry, I can see some of the students craning their necks. We're gonna raise this. Okay, so that's how we figure out the effective radius. In some cases, we can actually get this more directly, so I'll show you in a moment how we can do that. Okay, we're gonna keep that there, good. Okay, we can also figure out the mass of the star, and typically that's done using the fact that we can see stellar binaries. On Keplerian orbits. Okay, so there's a bunch of different ways that we have of observing stellar binaries. One of them is just, again, using kind of Gaia or some other astrometry that you can just literally kind of watch the positions of the stars kind of go like that. Okay, that's kind of the most obvious case. But you can also have what's called an eclipsing binary. So here's a little video to kind of illustrate what happens. So you got 2 stars, and if they're orbiting edge on relative to your point of view, then as one of them eclipses the other one, it's going to look dimmer overall, okay? So that's how that works. And actually, you can get a lot of information. So you can get information not only about, for example, from this length of time, you get the orbital period, but also based on the depth of these absorption troughs, you can get, information about the relative sizes of the stars. And if you know how fast they're going, then the width of that trough also tells you their radius. So a lot of information coming from that. Okay, there's also another type of binary that we can observe called a spectroscopic binary. And this is using the Doppler effect. So the fact that, when the star is coming towards us versus away from us, it's going to either be red-shifted or blue-shifted. So here's a cartoon video of what's going to happen. Okay, so we see the spectral lines are kind of shifting in this characteristic way over time. And that also gives us tons of information about the mass and some of the other parameters of the binary. Okay, so that's how we can get the mass. Actually, in more recent times, we can also get the sound speed profile, so CS as a function of R. And the way that we can do this is from astroseismology. Okay, so the fact that we actually have these missions, so the eclipsing binary story is actually one of the main methods we use to detect exoplanets as well as binary stars. It happens in the same way pretty much. But now we have all these experiments that are really trying to look for exoplanets. And so they're very, very sensitive to deviations in the light and how much light we see, and that's a function of the radius of the star. So if it's like pulsating, okay, that's going to change the luminosity, as we can kind of see over there, or the effective temperature that we observe, all these things. So yeah, we have missions like Kepler, which are doing astroseismology of tens of thousands of stars, and we can get this information. Okay, and the sound speed profile is actually telling us a little bit about what's happening in the stellar interior in terms of the composition, the density profile, the temperature profile. Okay, it's not giving all of those things to us in an unconstrained way, right? All of those things kind of depend on each other in some non-trivial way, but it's just providing us more information, okay? And that's a more recent thing. Okay, so what we notice when we look at some of the intrinsic properties of stars is that it's not random, okay? the properties of stars are actually super, super correlated. So you kind of see regions of measurement space that are really highly occupied and highly populated, and other regions that have basically no stars at all. Okay, so this is the plot again from Gaia. Magnitude is just a funny way of plotting the luminosity. Okay, this is the color as measured by some mechanism, but I think it's more helpful to think about the temperature of the black body on the surface. And we see this kind of structure over here. The stars that are here are called stars on the main sequence. Stars actually spend most of their lifetimes on the main sequence, about 90% of their lifetimes. And if you just think about if I'm just going to look at some population of stars at some random point in their lifetime, at some random snapshot in time, you're going to, the ones that you're going to see the most of are the ones that spend the most time in that position. Does that make sense? I don't know if I said that in a super clear way. I'm seeing nodding, so I'm gonna move ahead. Okay, so stars are actually born somewhere, they're pre-main sequence, but then they go to the main sequence, and they kind of stay there for, it depends. So up here on this really hot end, okay, these stars kind of leave the main sequence, within maybe tens of millions of years or something like that. Down here, these stars actually, the universe is not old enough for them to have left the main sequence. So they're born somewhere on the main sequence, and they pretty much stay there until they run out of fuel in the center. Okay, notably, they run out of hydrogen in the core. And then they start to leave the main sequence and go to this giant branch. You can kind of see, I'll jump. You can kind of see there's a little horizontal branch here, sometimes called the helium branch. Okay, this giant branch doesn't go forever. You have this tip of the red giant branch. You also have this white dwarf region over here. Okay, so we're going to talk about all of that. Okay, but it's just to start to familiarize you guys with these terms. So if we want to understand the dynamics of why is it that the intrinsic properties of these stars are clustered in this specific way, and what dictates their evolution as they go off, and turns out they go off and they kind of loop around down here like that. So what the heck? Where does that come from? So that's going to motivate us to start thinking about what are the dynamics happening in the stellar interior, and how can physics beyond the standard model impact those dynamics? Okay? Any questions about this before I move on? Yeah?
So do we only know about the mass of stellar binaries? And if so, how many of those do we know?
Great question. Yeah, stellar binaries are sometimes referred to as the Rosetta Stone of stellar astrophysics, because otherwise we really wouldn't have a good way of determining their mass. And it actually turns out that the main sequence is a mass sequence. Okay, so the mass and composition of a star are actually enough to uniquely determine where on the main sequence a star is going to actually sit. And if we didn't have measurements of the mass, we would be kind of lost. Sorry, the question, I remember this time. The question was, how many of these binaries are out there, and how necessary are they? The answer is they're very necessary. But luckily, a large fraction of stars are actually in binaries, and it kind of depends on what type of star it is. But it's around tens of % of stars are in binaries. So yeah, the fact that the sun is a singleton is not super fine-tuned, but it's maybe, it didn't have to be. Yeah. Cool. And yes, I do believe singleton is the technical term for a lone star. I don't know, I find that very whimsical. Cool. So now we're going to talk about the dynamics. We're not going to finish it today, so we're going to talk about it tomorrow, but I have it kind of written down in a way that's a little bit modular. So let's talk about pressure balance and see how far we get. Let's go over here. Okay. So let's talk about pressure balance. And that's probably the Easiest thing to understand, so I think we can finish it in 5 minutes. So given the fact that I'm telling you that stars are kind of staying put on the main sequence for, in some cases, tens of billions of years, it must mean that they're actually pretty stable, right? If they, would have, I don't know, collapsed into a black hole or something, right? It wouldn't have taken, tens of, billions of years. It would have happened. You can do the calculation. It takes actually around 30 minutes, okay, if you have no pressure. So we need pressure to support stars. So if I just imagine I have some little chunk, okay, chunk of my star, and it has a mass dm, okay, I'm going to go from a radius r to a radius r plus dr, all right? And I'm going to imagine that there's a pressure gradient, so I have some p plus dp up here and some pressure p there, okay? And the area of my little chunk is A. So I've got pressure pointing down, okay, because I've got a pressure gradient, and the way I've defined this, it's a positive pressure gradient pointing down. As I know, I've also got gravity pointing down. So right off the bat, in order to have stability, that kind of tells you that it has to be a negative pressure gradient. So as you go from the interior of a star and you move out, the pressure has to go down. Okay, so the pressure gradient has to point the other way. Okay. So how can I capture this dynamic? So first of all, I'm going to want to write the mass of my chunk in terms of the density, because that's more of a quantity that I can, characterize inside of a star. So I can write that as rho times A dr. Okay, where A, again, is my kind of cross-sectional area. And I can also figure out what is the enclosed mass, within this radius by integrating over that same density. So from 0 to r, 4 pi r prime squared dr prime times rho of r prime. Okay. And I only care about the enclosed mass because this is like Gauss's law of gravity or something, right? So having written things that way, I can write the force of gravity, okay, as minus g times the enclosed mass, which I have here, times dm over r squared, and it's pointing in the r hat direction with a minus sign, so it's pointing in. And at the same time, I have my force due to pressure, which I'm just going to write as minus a times dp, again pointing in the r hat direction. Okay, so these are my two forces. I can do Newton's laws. Okay, so you can combine these and get d squared r by dt squared equals minus 1 over rho of r dp dr minus g m enclosed over r squared. Okay, so all I've done is F equals ma, but I, moved around some rows. And again, usually we ignore this for the main sequence stars because, like I said, they're kind of lasting tens of millions to tens of billions of years. So it's a pretty good approximation to ignore that. And we say that they are in hydrostatic equilibrium. Okay, so if I can ignore that, that gives me a relationship between the pressure gradient that is necessary to support my star and the mass or density profile of my star. Okay, so there's a relationship there. And so then that raises the question, well, what are the sources of pressure that can be supporting my star? Okay, very schematically, I have a contribution from just the ideal gas law and KBT. Okay. Here, this plus sign is not a real plus sign, but I'm just showing you different terms that can be relevant. Actually, it turns out radiation pressure is super important in high mass stars in the main sequence. As we'll talk about tomorrow, higher mass means a higher internal virial temperature. Okay, so high mass means high internal temperature. So this is the radiation pressure. And then I can have different scalings. So I can have terms coming from degeneracy pressure, which scale like some number times the number density to the 5/3 times or divided by the electron mass, or it's some number times n to the 4/3 power. And this depends on if the Fermi velocity of your star is much, much less than the electron mass, or if it's much, much greater than the electron mass. So I've got ideal gas, I've got radiation pressure, and I've got degeneracy pressure. And usually one of these three things is going to dominate, okay? And for ideal gas, most of the main sequence stars, save for the really high mass ones, this is the most relevant term. Like I just mentioned, the high mass ones, this is the relevant one. And this is actually what supports, you may all know the white dwarf example or the neutron star example, but what you may not know is actually that some of the stars, actually as they just leave the main sequence, are actually also supported by degeneracy pressure, notably some of the red giants. Okay. All right, so that's where I'm going to stop for today with just telling you about pressure, but we haven't solved for the full dynamics. So tomorrow we're going to talk about energetics and how we're able to dissipate energy within the star, and that's really where BSM can enter, and it's all kind of coupled to everything, so we'll see how that plays into this. All right, see you later. I'm done.
Great, just about on time. So let's go get caffeinated and come back.
Yeah. Hi.
Question. So,
Yeah.
okay, just regarding the last statement, I failed to see why red giant would be dominated by the degeneracy pressure because I always
Only
thought
in
that
the
they
core.
expand-
Only in
only
the core.